Hi, I'm Danielle from the WSU Department of Chemistry, and today I'm going to be talking about the Voltaic cells post-lab. This is a help video for that. Alright, so the first post-lab question asks you to use the standard potentials from your textbook or from the experiment background to calculate theoretical cell potentials for those 3 cells that you constructed in lab. So I'm going to give you guys an example, and we're going to be using the copper-magnesium cell using the potentials from the experiment's background. So our standard reduction potential for our half cell with copper is going to be 0.34 volts, and a standard reduction potential for our magnesium cell is negative 2.37 volts. So the element that has the higher standard reduction potential is going to be our cathode. Reduction is going to occur at our cathode. The higher number signifies that it's more easily reduced than this magnesium, which has a more negative potential, so it's more likely to be oxidized. So that's going to be our anode. Over here in our equation for calculating our standard potential of our cell, which is our cathode minus our anode. So in this case, it will be 0.34 minus a negative 2.37, so we're going to end up with a total of 2.71 volts as our potential for this cell. So we're going to skip ahead a bit to the results and discussion section to question 2. It's asking you to write balanced chemical equations for the 3 cells that you constructed from your known metals. So we're going to use the copper-magnesium cell again for our examples, and I've written their half-cell equations from the reduction potential list that you can find in your background or in the back of your textbook. So if we have copper 2+, we add 2 electrons to get solid copper, and again, these are reduction half-cell equations. So when we are writing the equation for our full cell, remember that this is our cathode, our copper is our cathode, but our magnesiums are anodes. So we are not doing a reduction reaction at the anode, we're doing an oxidation. So we can't write our magnesium equation like this, we have to flip it around. So when we do that, we get our copper 2+ plus our 2 electrons gets copper solid, and then our magnesium solid, that equation has been flipped around, and then we get this equation down here at the bottom, which is the equation for our reduction-oxidation reaction for our full cell. And also notice that our electrons cancel out on either side. You always want to make sure that your electrons cancel when you're writing these equations. And if they don't, then you've done something wrong and you have to go back and figure out what that was and fix it. Question 3 in your results and discussion section asks you how close your theoretical potentials that you measured were to the actual cell potentials that you should have calculated. So when you're addressing this question, you don't have to use all 3 of these numbers and compare them individually. We're just going to ask you to compare the average cell potential for each cell that you measured and compare that to the theoretical value. So just sum these up and divide them by 3. So don't compare each individual reading. Again, just compare the average of these. And when you're comparing these, we're not looking for some profound scientific analysis, but do tell us whether your values seem very far apart or are relatively close together, and make a couple of suggestions as to why this might be. Question 4 on your results and discussion asks you what kind of factors may have caused your actual cell potentials to differ from what they theoretically should have been. So when you're addressing questions like this, you want to try to think of things in your experimental setup that might not have been ideal or perfect, because this is real life situations, it's not in a sterile lab, so things might have gone wrong. So some hints for you: think about things like your solution concentrations, how that might have affected your reactions, your electrical connections, what might have gone on with your electrical connections that might have affected something in this lab. Also think about your salt bridges and whether or not your metals were clean. And also your glassware, if you cleaned out your glassware properly beforehand or not. And when you're answering these questions, these are just hints. We want you guys to elaborate on this more than just saying, oh, my solution concentrations were off or something. We need more detail than that. So just make sure that you are giving us an adequate response and not just giving us 2-word answers like these right here. Question 5 is asking you to rank the metals that you worked with in order of decreasing standard reduction potential. So you're going to be using your data to tell when each unknown behaved as the anode or the cathode when it was paired with different known metals. So I've rewritten our standard reduction potentials for our copper and our magnesium cells over here, and then I wrote a random unknown number. Don't use this in your post-lab. I just made this up out of my head. I don't know if it even actually means anything. It's just random, so don't use it. This is just for demonstration purposes only. So when we're looking at these cells, if we constructed a cell using copper and this unknown metal over here, so our copper would act as the cathode, and then our unknown would be acting as the anode in this cell. But if we paired our unknown metal with our magnesium, our unknown would be acting as the cathode, and then our magnesium would be acting as the anode. So what this tells us is that the standard reduction potential for this unknown is somewhere in between that of copper and magnesium. As you can see, it's negative 1.67, copper is 0.34, and then our magnesium is negative 2.37. So it's somewhere in between those, and you're going to do these for each of those unknown metals that you worked with. And then question 6 is asking you to take everything that you know about these unknown metals, including physical appearances and their standard reduction potential ranking that you just constructed, and propose some identities for them. So it's probably still going to leave you with a few possibilities for each unknown, but you can do your best to eliminate everything that you're reasonably sure it isn't. So if we were trying to rank this between copper and magnesium, you'd be looking at all of the metals that are in between copper and magnesium for the potential for this. So you wouldn't be looking above or below magnesium, but somewhere in between. Once again, my name is Danielle. I'm with the WCU Department of Chemistry, and this was the Voltaic Cells Post Lab. I hope that was helpful, and thanks for watching.